so speed is the absolute value of the velocity. Next thing, you'll encounter questions in the homework that ask something like this. It'll say, what is the average speed of the particle? What is the average speed of the particle for some time period? So say for, I don't know, t equal 3 to t equal 9. What is the average speed of the particle from t equal 3 to t equal 9? Now that you know what speed is, and you've already learned how to calculate the average of anything, any function, someone just remind the class. How are you going to calculate the average speed? Heidi? So I find the absolute value of the velocity. That would be step one, because that will give me the speed function itself. 2 for Heidi. Once I know the absolute value, or I know the speed, what do I do with that speed formula? Yes, because we've learned that if I want to find the average of some function, I need to integrate that function. So if I'm finding the average value of the speed, I need to integrate the speed. There.
So you integrate it to find the velocity through all the different and divide it by 6.
Very good. So I integrate the speed. Integrating alone doesn't give me the average, but the integral combined with dividing by the width of the integral, that will give me the average speed.
So would we do anything different since we're talking about the speed and not the velocity when the graph dips below the x-axis and is negative?
Great question. Here's how that gets fixed, Landon. Everyone do this, please. 3 tickets for Landon. Go back to your calculator, get y equal, and in y2, we're going to graph the speed. So y1 is the velocity, and y2 we're going to graph the speed. So absolute value on the 84 is found in several places, but the place I like best is go just hit second and catalog. Catalog is item 0, or sorry, it's right on the 0 key. Absolute value is the first one in the list. So just press enter. And now I want it to be absolute value of y1. So say alpha f4, choose y1, small set. So we need help doing that. Oh, whoa. Inspire is different, but most people were able to find it. If you can't, just ask, I'll help you. Pretty good. Now if you do zoom fit again, you get 2 graphs. The velocity and the speed. Blue is the velocity, the red graph is the speed. Now they're pretty much the same graph, except that like Landon said, whenever the velocity is negative, the speed isn't negative. The speed's the same numbers or the same values, they're just positive. So. Do we need help? I think it's working. Don't use this graph.
Probably didn't work.
It did actually.
Really?
Let's have a chance.
I'm really mad last night, but I need to have this.
If it was NCAA, I'd be the mark, yeah.
Oh yeah.
Your wall is stronger than a girl's
Beat Utah. Un momento, por favor.
Don't try to talk Spanish.
Hey, I went to Mexico, so I'm fluent. I know more Spanish than you. Do you take Spanish?
Yes.
Then I don't know more Spanish than you. I do like three of Hey, Brayden, see you like dog
So bad. You wasted half
Hey, look up again. Look up. Look up. No one's up. No one's up. Just keep doing the steps. Those important, so you can make sure you learn all the keystrokes. I don't know why it's doing that. Got. Len, did that answer your question so far?
Yes.
Okay, so look back here. So if I integrate the speed, I'm going to get the if I do this computation, I'm going to find the average speed. So everybody do this and get a number for me. Come on, go. Need help, just stop as you're walking around. But get that done so you get a number for the average speed. That's going to show up in the homework for sure. And the test. So even though you're not getting the right numbers, Amanda, at least make sure you know where to find everything. Because you're very good at the calculus. I really don't want you to change calculators. You just got to, it's just, you could try that. Just won't go to radian mode. Like I can't get it to graph in radians, and it'll go wild. So.
Do you want to see how you lost it?
Actually, it would be better if I already set it up. Just leave it.
I got
It's our new invention. You know how much more entertaining a match would be if you had a dinosaur?
Quiet, everybody else. Silence.
use like F-Vex or like labeling graphs. You know how on the Inspire it says like F1 of X, you do not use that.
The rules specifically say you can't use calculator notation. So I don't want to say that you can, I'd be afraid they might dock you.
Okay.
So I would just always use FNG on your paper. And then it actually makes it easier when we're talking in class anyway, because all the 84s are saying Y1, Y2. So we're always just putting F in the 1 and G in the 2. So it makes sense. Heidi, please.
But for this one, you just put them VFT.
Oh, yes, exactly, because in this case, we have a specific symbol to represent the velocity, so V of T is
But
perfect.
if we don't, we name them F and G.
Correct. On all the problems that involve everybody, hey, the only time you're really gonna have to be naming things on the AP test is when they give you an equation that says like this, y equals something. That's the only time you're gonna have to say, oh, let's just call it out. For all of the other problems, like with velocity or motion or whatever, they'll give a name. So usually not big deals. Anybody else? Perfect. Okay, please, one person, please raise your hand and tell me what value you got for this. Let's go, Heidi.
1.172.
1.172?
Six.
6. And 2 points for Heidi, somebody help. What would be the appropriate units since that's required for this number, Len?
Meters per second.
Meters per second. If the velocity is measured in meters per second, the speed is going to be measured in meters per second because they're very much the same things. Only difference is the sign. How many got this before he said it? 2 points, 3 for Landon and 3 for Heidi. Any question? Okay. Next thing that's going to show up in the homework and the test is they may ask this question. Write this one down, please. They may say, what is the acceleration what is the acceleration of the particle and they'll give some times. Maybe they say at time equal doesn't really matter, we'll say 4. What is the acceleration of the particle at t equal 4? Okay, all of you already know how to do this using one method. Let's just give tickets to all of you to remember. So raise your hand if you feel like you know what you should do to answer this question. Raise your hand if you know. You all should know that this was unit 3. What do you do if you want to find the acceleration of the particle at t equal 4? So just a review question. How do we find the acceleration of the particle at t equal 4? Let's go, Sarah.
Find the derivative of,
So we find the derivative of the velocity.
yeah,
Once we have the derivative of the velocity, Sarah, what do we do with it?
I forgot what you did after that.
No worries. So if you find the derivative of the velocity, you'll have an equation for the acceleration,
Okay.
meaning you could find the acceleration at any time.
Oh, then you plug in 4.
Plug in 4 because we want the acceleration at time equal 4.
Yeah.
Perfect. How many knew that before she said it? 2 points, 3%. Any questions? Okay, look at me, look at me. Okay, on the AP test, there are sections where you are allowed to use your calculator and sections where you are not. So everything we've done up to this point were the sections where you have to do it without the calculator. So you can't throw away what you've learned. You still have to do it without your calculator. In fact, about 2/3 of the test questions must be done without a calculator. But they're also testing to see if you know how to do some things with your calculator. So this problem is showing up on the calculator section. So we're going to do it with our calculator. Here's how you do it with your calculator. Go back to here. Go to the main screen on an 84. Go clear. Get a fresh thing. Go Math 8. Okay?
I like it.
Type in X. I want to take the derivative of the velocity, which is in y1. So we go alpha F4, choose y1. I want to find that derivative at t value, or x in this case, of 4. Now I press enter, and I write down the answer.
I like it.
So I write down on my paper, the derivative of the velocity at time equals 4 is exactly the same thing as the acceleration at time equals 4. That's equal to a negative 0.910. We must include the units. Acceleration is the rate at which velocity changes. That means the velocity will be changing by this many meters per second every second. This is what you have to have on your test to get full credit for this problem. Please, Kelsey.
How do you do it on green screen?
It's really close. So go math 8.
Yeah.
Do the variable thing to get the y1.
Okay.
Good to there. Just do comma x,
Okay.
comma 4, close parentheses. Perfect. Please.
Did you put meters per second squared?
Either way. So meters per second every second or meters per second squared, both are fine. Plan.
How about the Inspire?
On the Inspire, what you're going to do is there's a key on the Inspire that pops up a box that has a
Yeah.
whole bunch of like.
So
you got that one?
I got
Perfect.
that.
So you find it's on the bottom row. No, don't do the bottom. It's like on the second row. There's a derivative symbol. Choose
Yeah.
that one. Got that?
Yep.
It's a little tricky now. You put an X where the X goes, right?
Yep.
Now you're going to hit the variable key to get your function list. You're going to choose wherever the velocity is. Okay. Got that?
Yep.
Put an X inside of that. You got that one?
Yep.
Now you're going to move over to the end.
Outside of parentheses.
You got to do the bar now.
Okay.
So you got to get it to type this thing, this bar. You find the bar on your little, on the equals. Hit that
It's the second.
second function equal, I think. There you go. Thanks, Emily. Good work.
And then you have to write x equals.
There you go, X equal. Welcome to the world of the Inspire.
Yeah.
Sorry for sarcasm. Ouch. It's not my favorite calculator. It's like, I get that it does lots of things, but man alive, it takes so many keystrokes.
Okay, I got it.
Nice.
Still takes the same number of keystrokes.
Actually, fast.
It may be fast with the keystrokes, but it's still, I can do everything on the 84 faster than you can do on the Inspire. I'll race you anytime.
Okay.
Right now. Did you get to work?
I don't know. I think I'm pretty.
Landon,
Yes,
it worked.
yes, I did.
Okay. Quiet. Silence. Okay, does anyone have a question how to get this to work still? This is going to be in the homework, so make sure it's working. Everybody good?
So what is this?
Oh, sorry,
for
Lexi.
again? Like, what is this
So
showing us?
what we did, is we took the derivative
Yeah,
of the velocity,
okay.
we took the derivative of the velocity at specifically t equal 4, which means what I wrote here, Lexi, I found the derivative of the velocity at time 4, which is the same thing as the acceleration of the the acceleration at time 4, which is what they were asking me to find. Perfect, 2 points. Anyone else? Again, get used to FRQs. On the test, you have to write things down. You can't just have a result, okay? You have to have units. Any questions on finding this? In the homework tonight, there'll be a few questions similar. Just use your calculator, okay? Just use your calculator. Next thing that kind of shows up in the homework. Let's go over here and paste the new one. Okay, this question shows up in the homework. I want everyone to be able to answer it. When, this is on the test as well, when is the particle moving to the left? And then it'll say something like this, give a reason for your answer. Okay, someone in the room, we've already talked about this one. Someone in the room, just explain in kind of common sense words, how do we know when the particle is moving to the left? We've already talked about it. Jackson, the velocity is negative. When the velocity is negative. So on the test, when you write down the answer, that's all you have to write. Now you do have to use your calculator to find this time and this time using the zero function. You've also got to find this time using the zero function. So just wave at me if you need me to show you how to use the zero function again. So everybody find these times using your calculator. Go. Find times using the zero function on your calculator. Just stop me if you need help. Find those times using the zero function on your calculator. Are we doing the velocity or are we doing the speed? Oh, can you erase it? Yeah, you can turn it off. So, sorry, I didn't understand the question. No. Oh, that's better. Oh.
How do we write it?
That's what I'm shooting just a second. Thank you. They grabbed it now. What did you do? What did you do? Did you tell us? Put it flat so you can see. Hold on, so you gotta come up. When you set a setting, when you get the setting, you have a sticker for you. Two different places for setting.
And then I also took a photo.
You're good. I knew it was meant to be gradient, we just couldn't find the set. Find another place. Thanks, Jeff. 3 tickets for Jeff. All right. Raise your hand if you found the zeros, please. Raise your hand if you found the zeros. Look at me. Raise your hand, I'll pay you. Raise your hand if you honestly found the zeros. What are they, Chad?
3, 6, and 9.
Good. I made the problem really easy to talk about on purpose so it's easier in class. Be aware that on a real problem, they often come out to be some decimal value and you need to store those. You cannot just write them down. You have to use the stored values when you're doing computations. Everyone hear that? Okay. How many got it? Show me. 2 tickets, 3 for Chad. Okay. Here's how you'd write the answer, Heidi. You would say, particle moves left. For, let's see, times that are between 3 and 6 and 9 and 10. So that's the answer. We have to give a reason.
Can you do it with like the closed bracket, 3, 6, like another closed bracket, or would they not have bracket?
So this is valid. Here's another way to write it. I'll just write it down to make sure you see it. So the particle moves left for intervals. And then you can do exactly what you said, Kelsey. 3 to 6 and 9 to 10.
Would it be parentheses or closed brackets?
You can answer it. I'll just give you a little hint. Right at 3 is the particle moving left, right, or is the particle stop? Stop because the velocity is 0. So don't really technically want to use a bracket because the particle is only moving left, not after. Does that make sense?
Yep.
Please, again.
What about at 10? Because technically it will contain.
Oh, that's very smart.
But is that because you can't find the second point and it's just not different?
No, technically, you would say that it goes like this. They've never been picky about that. So it's never been an issue. But technically that would be better, for sure. Anybody else?
Wait,
Oh, I heard a voice, please.
for the 3 and 6, is it supposed to be a parenthesis or is it supposed to be that bracket?
For the 3 and 6, it really should be a parenthesis because right at 3, Sarah, the velocity is 0. And when the velocity is 0, the particle isn't moving at all. I can say with some confidence that if you put brackets, I don't think they'll penalize you. But it's always best to not take a chance that you end up with some grader that's kind of picky. So. Anybody else? Perfect. You have to give a reason. Here's the reason. It's really simple. Just don't forget to write down the reason. Particle moves left for these time periods because, or since, v of t I could write the words is negative if you want, or a short way to write is negative is this, is negative. Wow.
Oh, I wonder.
V of t is less than 0, that means V of t is negative. Does that make sense? So you say the particle moves left during those time periods because V of t is negative for those time periods. Something like that. No penalty for a diagram to do that. Okay. You don't have a question about how to answer this on a test. Give you a couple of practice problems and homework. Go ahead.
So on this, do we write 10 just because that's like the end of the, like the graph would keep going down, but because that's like the.
Yes, very good. I didn't write all the words that would typically be on a test question. The test question would have said, for the time period 0 to 10,
Okay.
Identify the time periods or the intervals when the particles are moving left.
So you would just keep it.
Good question. 3 tickets. Anybody else? Awesome. Okay, next thing. Okay, new page here. Hold on. Okay, we've already talked about this idea, so this is a bit of review. We have talked about that if I integrate, let's say from 0 to 3, the velocity. Okay, I'm going to say, look at me, focus hard. They said we get to the point of the discussion where we would be discussing an idea that if you thoroughly understand this idea, along with what we've already learned, you're on track for a 4, guaranteed. We're at that point. I've come up with a phrase that I feel is helpful in remembering this big idea. Here's the phrase. Just listen to it. If you feel like you'd like to write it down, I'll give you time to write it down. If I integrate, look at what I'm pointing to. If I integrate the rate at which the position is changing, velocity is the rate at which position changes. So if I integrate the rate at which position is changing, I will find how much the position changed. So I tried to wordsmith it in a way that makes it easy to remember. If I integrate the rate at which position is changing, position is changing, never thought of that. I will find out how much the position changed. What I've said before is if you integrate velocity, you get the change in position. Those two statements mean the same thing. So we want to write that down. If you integrate the rate at which position is changing, you will find out how much the position changed. Honestly, that idea, it's called the fundamental theorem of calculus. There's nothing that is more heavily tested on the AP test than that single idea. Yeah. If you integrate the rate at which the position is changing, you find how much the position changed.
So, the fundamental theorem of calculus is, you kept saying it was like the back door, and that's why that like derivatives. So because of this is why derivatives work.
It's the fundamental theorem is the connection between derivatives and integrals.
Oh, okay.
Yep. It's the bridge that links the two halves of calculus. Yeah. Oh, I have Ice Ice Baby at home now. I just gotta get that on my ear.
Oh, I'm excited. I'm excited.
I couldn't resist. I don't really like the song, but you kept asking for it. So. Don't like it. The rhythm's catchy. The rhythm's catchy. The lyrics are like, what? Okay. Any questions? Do this on your calculator, please. Give me a number. Go. Come on. Do this on your calculator. Give me a number. Do this on your calculator. Give me a number.
2.224.
There we go.
Wow.
Yeah.
And he's on an flyer too.
Oh.
Yeah.
We already had it typed in.
3 for Landon. Somebody tell me what will the units be? Looking for him. What What would the units be in meters? We're finding the change in position. So at a great velocity, you get a change in position. Make sure you can get that to work on your calculator. You were having trouble? Okay. Next connection here. Okay, we've talked a lot about how when the calculator integrates, all it's doing, it's taking the value of the velocity multiplied by some small change in time. So for example, as the calculator performs this integral, it's moving across the velocity plot, getting values of velocity multiplied by small changes in time. So like right here at 1, the value of the velocity is this point, which means the value of the velocity is also the length of this line. I missed the spot, but close enough. So the calculator takes the length of that line, multiplies by a tiny width, and calculates the area of that red rectangle. Like the problem isn't about area. We're not talking about area, but it just happens. Like when we integrate velocity, it finds the area of that red rectangle for that one tiny amount of time. It then does it repeatedly. So it does it for another thin rectangle. And it does it again. And it just keeps going until from 0 to 3, it's found the area of all the thin rectangles. It adds them all up. Therefore, it is computing, without us really even thinking about it, the area that I'm now highlighting in purple. So, question for the whole room. What I just explained about how when we did this integral, we weren't talking about area, but it just happened. This number turns out to be exactly the purple area because of how integration works. Give 1 or 2 if you feel like that makes sense. 1 or 2 if that makes sense. So the 2.224 has 2 meanings now. It is definitely the amount that the particle's position changed by, but it is also the area of the purple. 1 or 2 if that makes sense. Come on, show me. 1 or 2 if that makes sense. It's also the area of the purple. 2 tickets for the room. Don't forget that connection. When I integrate this velocity, I get the change in position, but this area corresponds to that number.
Will that only work when we're working with velocity?
It'll work with any function. You're integrating just a function alone. Like it's not like one function subtract another or something more complex. But any function alone, when you integrate that function, even if the problem isn't talking about area, you're finding area as well. Okay, it doesn't have to be just velocity. Please.
So a calculator does the GT calculations for us, but didn't Isaac Newton like invent calculus? And so how did he do it?
Yeah, we're just not there yet.
Is that what we're
getting there.
Ian,
You're doing just fine. You're doing just fine. Unit 5 is when we'll discuss that. So.
Oh, okay.
Yeah. I picked the order for a specific reason based on doing it lots of different ways, and this has been the best. So.
Yeah.
So it's like any position of the area, it's only one, small.
1 second, Deborah's right on. Hey.
Is the change in position the same as area if only one function is involved?
Yeah, if you're just integrating velocity, so the area of the velocity plot absolutely represents the change in the position. So you can look at this velocity plot and say, very interesting. Let's just get the whole class to answer this. Just look at the picture and tell me, we'll call this area number 1, we'll call this area number 2. Just show 1 or 2 if you can tell me which area appears to be larger. It's pretty close, but I think you can tell. Just give me 1 or 2 if you can tell me which area appears to be larger. 1 or 2 if you can see whether the area here or here, it's pretty close. Here it's a little closer than I thought it was. So people were saying 1, some saying 2. Let's find out. Do the integral from 3 to 6. It was visually closer than I expected, so we'll do the integral. Do the integral on your calculator from 3 to 6. Do the integral on your calculator from 3 to 6 and find out. What'd you get, Soren? Soren, you did? No? Okay. Somebody's got it. Heidi. How many have that, please? Show me your hand. Show me your hand. 2 tickets, 3 for Heidi. please note an important thing. Area isn't negative, area is always positive. The integral comes out negative though, and it has to come out negative, because all the calculator is doing is taking all of these velocity values, represented by these vertical lines, and it's multiplying them by some small amount of time. But every value is a negative value because the velocity is negative throughout this region. That's why you get a negative number for the integral. One or two if that made sense. Come on. One or two if that made sense. That's why we're getting a negative value for the integral. 2 tickets for the room. But mentally, Deborah, you think to yourself, okay, I know this area. The area is a positive value. It's 3.002. But because that area is located below the horizontal axis, I know the particle actually changed its position to the left. Okay. Questions? Please, Jim.
Why is it that the area, the distance that it changed and the area are the same?
It's all because of how the integration works. So when the calculator does the integral, it simply takes, starting at 3, the value of the velocity multiplied by a tiny amount. Eventually it gets over to kind of here, where the value of the velocity is this number, but because of how graphs work, that velocity value is the same thing as the length of that green line. So it takes the length of that line, multiplied by a small amount of time, finds a small area. Does that answer your question?
Yeah.
It does it repeatedly for all of the thin lines. Integration means add them together, it adds them all up, so it's finding the whole area. Perfect. Please,
So I just want to make sure I'm like getting this. So it's negative so that you know that it's to the left, but the area is just a positive 3.0.
Perfect. Yeah, when we speak of area, we always speak of the area as being positive, but it's crucial that you say, yeah, I get the area is a positive 3, but the velocity was always negative. The particle was for sure going to the left. For sure going to the left. And that's why the integral is negative. Because when you integrate velocity, it's back to, I forgot who asked, but when you integrate velocity, you're not finding area. You're finding the change in position. But they do correspond to each other. Does that make sense? Any questions? Oh, please, Lynn.
So if you were to integrate acceleration, you would find the change in velocity, right?
Everyone hear that? 5 tickets. Velocity is the rate at which the acceleration is changing. So my little phrase comes into play. If you integrate the rate, it rhymes. I thought that was nice. If you integrate the rate, at which the velocity is changing, you get how much the velocity changed. It's perfect. So if you integrate acceleration, you find out how much the velocity changed. If you integrate the rate at which anything is changing, you find out how much that thing changed. That's the fundamental theorem.
Wait, but if you add the negative and the positive, then you know from starting position how far to the left it has moved or how far to the right it has moved.
Nice.
And so you can like model, oh my goodness, you can, oh, that is so cool.
Nice.
What did you figure out? It's like pictures of great.
If you, wait, do you have to, okay, just teach.
All right. Sweet.
Okay, I got it.
Okay, watch. Watch,
That's
watch,
cool.
watch.
Yeah.
So here's what Ian's noticing. Everyone else in the room can see the same thing. It's not hard. I can find, with the data that is on the board, I can tell you, like I probably have to use my calculator because the numbers are decimal and I don't want to do it in my head. But simply by adding or subtracting or a combination, I can tell you the value of this integral. I do not have to do an integral. How many know what I'm talking about? Raise your hand. Show your hands. Come on. Who knows what I'm talking about? So what do I do, Bailey?
You add them together.
Yeah, so do it for me on your calculator quick, Bailey. What do you do?
It's negative 0.778.
-0.778. It's perfect. Look, from time 0 to, this is what you're saying, right? From time 0 to time 3, the particle moved about, here I'm the particle again. I go kind of 2, let's see, there's 2, then just a little bit meters to the right. But during the next 3 seconds, I go 3 meters that way. So 1, 2, 3. So my overall change in position is only this small amount.
Cool.
even though my distance traveled was a lot more.
Yeah.
One or two if that makes sense, come on. One or two if that makes sense. One or two if that makes sense. Let me just say it one more time. So this is saying, so during the first 3 seconds, you know, everyone look at me, eyes up here, come on, eyes up here. Crucial thing. When you integrate velocity, you never, ever, 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 have I said it enough?
No.
One more time.
Ever.
There you go.
One more.
Ever.
Oh, there we go.
When you integrate velocity, you never ever find position. Got it? Memorize it. When you integrate velocity, you never find position. What do you find?
Change.
Change in position. Okay, good.
You almost better watch it.
Almost. That's how I broke my hand last year. It was this time of year. I got so excited. Okay.
Do it.
No! Never again.
Never, ever,
It's not
ever
working.
again.
Never ever again.
Do it if you're cool.
No, but you know what? Okay.
I don't know what.
Don't do it, I promise. You won't be happy. But, so we know that during the first 3 seconds, the particle was somewhere. You don't know, nothing, I've never told you where the particle was. The particle was somewhere. During seconds 0 to 3, it moved to the right because its position changed by this amount. So the particle was somewhere, maybe it was here. It ends up moving 1, 2.224 this way. Then from 3 to 6, we looked at the graph of velocity and say, hey look, velocity is always negative. Indigo confirms that. The particle now goes from where it is now at time 3, that way. 1, 2, 3 meters. The net result is, it's about that much to the left of where it was when it began. Okay? You're fine. 1 or 2 if that makes sense. If it's still 2, it's okay. 1 or 2 if it makes sense. 2 points for the root. Okay. Oh, please.
So adding the area will find the change.
Listen to Chad. Listen to Chad. 3 more points. Hey. So if you have a velocity graph, and there are going to be some problems in the future like this, not yet, but you're going to see them. And they give you the areas of the velocity graph, you know exactly how the particle's position is changing. Yeah, perfect.
Okay, so it's probably.
No, it's not.
Okay, so you're saying like, I get why it finds the change in position, but isn't negative 0.778 meters also just the position between that interval, because it's moving to the left, not left, right?
It's a change in position.
But it says you can't find the position, but you did.
No, let me demonstrate. The particle could have been here. This would be the particle's position.
Yeah.
6 seconds later, the particle is 0.778 meters to the left.
Of that, this one, we don't know that.
Right.
Okay.
The particle could have been here. Got it now?
Yeah.
Perfect. No, that's why I said you're not finding position.
Yeah.
You're finding how much the position changes. Please, Haley.
So, what type of question was this?
No, it's perfect. You're fine. You're fine. Hey. Hey. Typical questions. I got to check my list here. Hold on a second. I get kind of excited. I forget what we're even doing. Okay, we're pretty good. Look. It's not super common, but I have seen questions on the AP test that literally say, from time equals 0 to time equals 6, you know, how much did the particle's position change? There's the answer. Well, does that make sense so far? Okay, but I've also seen questions that ask this. Let's see. At t equals 0, the particle's position is, this is going to be on the homework. At t equals 0, the particle's position is, let's see, x of 0 is equal to 1. We talked about this before Christmas. Okay, I'm now drawing a picture. I am not drawing a graph. This is not a graph. This is a picture. Okay? This is called the origin 0 on the picture. It's not a graph. Oh, yeah, you remember Raoul? Yeah. So 0 here, and then here's position 1 on the picture, and this is where the particle is located when time is equal to 0. So this little statement and this picture are the same thing. Maybe one or two if that makes sense. So the picture and the statement mean exactly the same thing. One or two if that makes sense. 2 points for the room. So Haley, what they'll ask you is they'll give you this information. They won't give you the picture usually. Then they'll say, find the particle's position at time equal, and we'll just say 6. Find the particle's position at time equals 6. Raise your hand if you can find it.
Oh my goodness. Oh my goodness.
Raise your hand if you can find it. And you don't have to tell me the number, just tell me how to find it. Who knows how to find the position of the particle at time equals 6 based on what we've discussed? This is the fundamental theorem. This is the key to the test. There's so many questions about this. So many questions. How do you find it, Lexi?
So you would take from 0, like the negative 0.778, how much it changed, so you do 0 for time equals 0 to that 1 plus negative.
Perfect. I'm sitting here at 1. I know that my position went left by this amount. So all I have to do is say, let's see, 1 is where I am, plus my position changed by this amount. Now, Lexi and everyone else, remember, on the AP test, you must store these values. You cannot use the rounded version, you use the stored version. But once you do the computation, somebody quick do the math for me. I don't care, Bailey. 0.222 is the particle's position. So, 3 2s?
Yeah.
So, that's how you find where the particle is at time equal 1. Please, Kelsey.
So like in an FRQ for the like word, would you say 1 plus B,
Oh, good comment.
like for the story?
Yes, like what you would do is you would have done this integral. You'd find this, you just go like this. So the grader knows that you've stored it. And then down here, you can write the number or the letter, it wouldn't matter. It's just important that you are using the stored value.
In your calculator?
Yeah, that's perfect. Oh, please, sir.
So if you said, if it was asking for particle's position at t equals 3, then would you do 1 plus 3.224?
Nice. Here's what Sarah just said. Here's another way I've seen the question asked, Sarah. They'll say, if x of 0, the position at time 0 is 1, find x of 3. And what Sarah just did is perfect. She says x of 3 is equal to basically 1, watch this, plus the integral from 0 to 3 of the velocity. Because 1 is where the particle is located, and the integral will tell you how much the position changed. You just type this in your calculator, and you will get exactly, what was the number? 224, right? So you're going to get 3.224 meters. Say your question, sir. Give me 1 or 2 if the purple makes sense. Give me 1 or 2 if the purple makes sense. This is on the homework for sure tonight. 1 or 2 if the purple makes sense. Perfect. Questions, Chad?
Well, can you teach us how to store just like a value? Because I know how to do it on the graph.
No worries. If it's a value that you've computed, it's just sitting on the main screen,
Yeah.
just hit Control Store. It should say something about answer storage. Did that work, Amanda? Should check. Please.
So is the purple, like, assuming that x of 3 is 1?
Oh, because no, sorry. The purple's assuming that x of 0 is 1. Is that what you meant?
Oh, okay, sorry.
No worries. That makes sense. Yeah, you guys, please, Chin.
So if you were just given a formula and you didn't have the graph, is it possible to find the total distance it traveled without the graph?
Yes. Everyone listen, hey. Okay, listen close, listen close. I've got to pass this out with the bell rings. I'll answer Chance's questions and pass these out. Listen, we didn't quite have time to hit everything in the packet. We hit most of it. So you're gonna get a text saying which problems to work on, like we've done before. Okay? But to answer your question, Chance, it's actually pretty easy. We have a graph of velocity, right? Particles move left and right, left and right. If we graph the speed, however, it's like forcing the particle to only go one direction. So if you integrate the speed, you find the total distance traveled.
Okay.
Does that make sense?
Yeah.
Good job today, everybody. Well done.
Oh, you're not missing
Like when you're playing tag and you make it straight, and you go tag, and then you want to walk around, or make it to face, what do you say? I don't know, we played it. I know we do it. Whoever made it was so annoying, you know, they make it so they just think that everyone has to make it.
We're so close.
I like you rejected it. Putting on the back part is so difficult. Second hand.
What they're trying to teach is that you use a calculator to get the most accurate answer as possible from the calculator. You don't want to use a rounded value later. You want to use the full value. But I was only showing you 0.778. It's storing a bunch of numbers. That's why.
Okay, it's so freaking close. You can find the change of position anywhere.
Yes.
You can find the change in position.
You can find the change
You
in.
can't find the origin.
That's correct.
So like when you derive something, and then sometimes numbers just disappear.
Yes.
Because when you derive it, how do you get that back?
You can't.
You can't.
So
So
you have to have other information.
otherwise you can't.
That's
Or
right.
you can just call that zero and just.
Well, you can do that,
right?
But that whole idea is, you said it perfectly. So, because the integral only gives you the change, it's because of what you said. When you take the derivative, if there's a constant on the end, it's gone.
It just disappears.
And you don't have any idea what it was.
And that's why I have to do x equals
Yes.
0. But I have a question. How
So
the
once you
frick-
know, once you know that x equals 0 equals 1, you can get back to the original position formula.
Okay, what is, but do you have to like, so I know those are just definite integrals, and you have to do an indefinite integral. And that's where things start getting a little bit crazy. But the indefinite, how does that all of a sudden make an equation? Is my question.
Oh, basically they just figure out ways to work backwards. They said, okay, here's how the derivative occurred. How do we kind of undo it?
And then you just have to do the
Yeah, that's why I like the word integral and antiderivative.
otherwise.
The other way is to be confusing. Like, so this is,
Yeah.
you're right, this is called a definite integral, and the other is called an indefinite integral. I prefer the word, this is an integral, the other is an antiderivative. Because the processes, even though they chose the same symbols, and even though they're interrelated, processes are distinctly different.
But, okay, and so you just undo the original
The derivative.
equation when it's okay. It makes sense! See, that's
You
why I
just
bang
put
my
it all
head
together
on
or
the table.
something?
What's that?
You just put it all together?
Yeah, very well. Nicely done.
Right. I would like to think the Academy.
Good work, man.
Thank you, Mr. Smith.
See ya.